All right, let's go ahead and get started. I want to welcome you back to Unit 15. This is acid-base equilibrium and buffers. I asked you last time to look at a couple of different problems and see how you could do. And so let's take a look at this one right here. It says calculate the pH of 0.700 molar sodium acetate solution. They give me the Ka for the acetate ion as 1.8 times 10 to the minus 5. So the first thing to ask ourselves is, what are we trying to get the pH of? Are we trying to get the pH of a strong acid or base? Are we trying to get the pH of a weak acid or base? No, no, and no. The answer is we're trying to get the pH of a salt. So that's going to involve a hydrolysis equation, and it's going to result in a Rice table. So we're going to ask ourselves, remember, when we're doing the hydrolysis for the salt, we're going to ask ourselves, which is the ion for the weaker salt, or the weaker parent, rather. So this came from sodium hydroxide and acetic acid, right? So acetic acid obviously is the weaker parent. So the acetate ion is the one that's going to be the ion from the weaker parent. So let's undergo a hydrolysis then. So we say plus H2O. And which way does the hydrogen move, or the proton move? Obviously, it's going to move from the water to the acetate, like that, right? So now we've got our reactants in equilibrium with our products. We've got OH minus plus acetic acid, HC2H3O2, right? So now let's fill in the initial concentration line. We've got a 0.700 molar acetate ion concentration. Water, of course, is not involved. We got 0 and 0, and the nice thing about these hydrolysis reactions is it's always minus X right there, plus X, plus X. We don't have to worry about coefficients or anything like that. It's always that, right? Now, we've got on the equilibrium line, 0.700 minus X, 0 plus X, 0 plus X on the equilibrium line. So we've got our Rice table. The next thing we're going to need to do is we're going to need to write our expression. Now, this is important because of the fact that when we write our expression, again, it's products over reactants, right? So it's K is equal to something. But what's important about the K? Is it Ka or Kb? Well, remember that it's hydroxide that's being produced, right? That means the expression is Kb is equal to OH minus times HC2H3O2 over C2H3O2, right? Make sense? There should be a minus right there, sorry. So the point is this. What's important is they're giving me a Ka, right? They're giving me the Ka for acetic acid is 1.8 times 10 to the minus 5, but I've got an expression here for a Kb, right? How am I going to resolve this? Well, this is the way I'm going to do it. I'm going to remember this, that Ka times Kb is equal to Kw. Okay, that's important. And Kw is 1 times 10 to the minus 14. So I can rewrite that as Kb is equal to Kw divided by Ka, or I can just write that in the expression. 1 times 10 to the minus 14 over 1.8 times 10 to the minus 5 is equal to x times x squared over 0.7. Notice again, since this is, I can say that this x is negligible, and I can just put a 0.7 on the bottom and get away with it, okay? All right, so now what I'm going to do is I'm going to solve for my x. Now remember, my x is my OH minus concentration, and so my OH minus concentration, if I do the math, I get this number, 1.97 times 10 to the minus 5. Okay, make sure you get that number. So I just put take the 0.7, pulled it up, did the necessary division, then take the square root. I get 1.97 times 10 to the minus 5. How many significant digits? 3. That means in my POH, be careful here, it is a POH, 3 significant digits means 3 numbers to the right of the decimal. I get 4.705. They're asking me for the pH, so I'll subtract that number from 14, and I get 9.295 for my final answer. Okay, 9.295 for my final answer. Now, let's go back and see if it makes sense that this should have been a base, right? When this dissociated, it should have been a base. So I had NaC2H3O2. What were the parents? The parents were sodium hydroxide and acetic acid. Acetic acid is weak. Sodium hydroxide is strong. Therefore, I should have gotten a base, and that's exactly what I got. I got this value of, let's scroll down. I got this value of 9.295, okay? All right, another problem I asked you to look at was number 16, and this one said this one said calculate the pH of the following salt solution, and it's 0.777 molar ammonium chloride. So you know it's a salt, so if it's a salt, it's going to be a hydrolysis, right? It's going to be a hydrolysis. So let's first of all, I tell you what, before we even start, let's try to predict whether it's going to be an acid or base, right? And see if our answer matches up. So we've got NH4Cl. So that means we had NH3 as the parent, NH3 and HCl. HCl is strong, NH3 is weak. That means I'm going to make this prediction. I'm going to make the prediction that this one's going to be acidic. Okay, I'm just going to put that right there, just in blue, so that I can go back and refer and see if that's going to be the case. Okay. All right. So what's going to be then the ion that's going to be involved in this hydrolysis? It's the ion of the weak parent, so it's going to be what? It's going to be NH4 plus, right? NH4 plus. So in this hydrolysis, I have NH4 plus H2O in equilibrium with NH3, right? Because the proton is going to go this way. The Bronsted-Lowry acid is going to contribute its hydrogen to the H2O. So we've got NH3 and H3O plus on the right-hand side, right? So now let's finish fill in our table. 0.777, nothing for the water, 0 and 0 for the change, minus x plus x plus x. Isn't it beautiful that it's always that? We don't have to worry about that line. That's one less thing we have to worry about, right? And then the equilibrium line is going to be 0.777 minus x. We'll call this minus x negligible, okay? Negligible, all right? Just like that. We've got an x and an x on the NH3 and the H3O plus respectively. All right. So now let's write the expression. Now, is this going to be a Ka or a Kb? Well, by the way, I'm not giving either one. I'm not giving the Ka or the Kb, right? So I just want to tell you that the Kb for ammonia is the same as the Ka for acetic acid. I looked it up. You don't have to worry about it. It's 1.8 times 10 to the minus 5. We'll talk about that in a little while. But here's what I want you to know. You're producing H3O plus. So the equilibrium expression is going to be Ka is equal to the concentration of products over reactants. So we have NH3 times H3O plus over NH4 plus, right? Now what we're going to do is since we've got Kb, not Ka, I'm going to say Kw over Kb is Ka, right? From the fact that Ka times Kb is equal to Kw. So I'm going to say that's 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5 is equal to x times x. That's x squared over 0.777. Remember, I got rid of this x because it was negligible. And I solve, all right? So you do that on your calculator, and when you do that, you're going to get this number. Check me on the calculator, but you do it. 2.08 times 10 to the negative 5. That's your hydronium ion concentration, your H3O plus concentration, to 3 significant digits, by the way. And so let's do the pH. pH is equal to minus the log of the hydronium ion concentration. When you do that calculation to 3 significant digits, that's 3 numbers to the right of the decimal, I get a pH of 4.682. Now, did that jibe with our initial belief about whether it was acidic or basic? Let's go back up and look. Yep, we said it was going to be acidic. It was indeed acidic. The pH we calculated to be 4.682. 4.682 is acidic, obviously, so we're on the money. All right, let's take a look at this one right here, and then I'll have you do one on your own. We've got 0.0345 molar KCl. I wish I had not scrolled down so far because I wanted to ask you this question. First of all, what are the parents? What are the parents? Well, the parents are as follows. They're KOH and HCl, right? KOH and hydrochloric acid. Potassium hydroxide, HCl. Strong acid, strong base, nothing happens. No hydrolysis. All you're going to have is you're going to have water, right? And the pH of water is going to be 7. All right? So that's that. There's nothing to do. That's it. You're done. Okay? So let's go into the last one. And this one I want you to do on your own. But here's what I want to tell you. I'm going to give you a little help. I've looked up the Ka for acetic acid. It's 1.8 times 10 to the minus 5. And I want you to do this one. We've got a 0.411 moles per liter of potassium acetate, KC2H3O2. And here's what I'll even do for you. I'll give you the final answer so you can check your answer. The final answer will be 9.179. 9.179. Folks, that's going to do it for this one. I'll see you on the next one. Thanks. Bye-bye.